Hello students, welcome to Shri classes. We have completed chapter 13, magnetic effects of electric current in all respects, that is the conceptual discussions, and in this lecture number 6 we will go through question answers, in text questions and exercise questions. So let us see now in text questions. Why does a compass needle get deflected when brought near a bar magnet? Compass needle is also a small magnet. Bar magnet produces magnetic field lines. When the compass needle is brought in the vicinity of the bar magnet, it experiences a force, magnetic force, and the magnetic force deflects the needle. That is the answer for this question. Next question. Draw magnetic field lines around a bar magnet. List properties of magnetic lines of force. Why don't two magnetic lines of force intersect each other? So we'll see one by one. Draw magnetic field lines around the bar magnet. This is the diagram which you can have a look at this. I hope you are able to see this, or let me, it's okay. I think you are able to see the cursor and the mouse. This is field lines around the bar magnet. Next question in that is, list the properties of magnetic field, magnetic lines of force. We'll go through that now. Here we have discussed properties of magnetic field lines. I hope we should be able to read this clearly. Magnetic field lines are closed continuous curves, first property. Magnetic field lines are directed from north to south externally and south to north internally, second property. Third one, magnetic field lines never intersect. Fourth one, magnetic field lines are crowded near the poles, hence the field strength is stronger at poles. The fourth point can also be framed something like, if the density of the field lines is more, then the magnetic field strength is more. That way also you can list the property, the fourth property. So these are the four properties. And finally you have one more question, that is, why don't two magnetic lines of force intersect each other? So how do you answer this question? Here I have already taken that. Here, why no two field lines intersect each other? No two field lines are found to cross each other. If they did, that means if the two magnetic field lines intersect each other, then at the point of intersection there must be two directions. So for a compass needle to point towards two directions at the point of intersection, it is not possible, and hence no two field lines intersect each other. So this is how the textbook answer is given, which you can note down. Next. Here you can see the Maxwell's corkscrew rule with the star they have given. I hope you understand that. Already we have discussed a lot on that. So here we have a questions once again. I hope it is clearly visible. Consider a circular loop of wire lying in the plane of the table. Let the current pass through the loop clockwise. Apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. If the current flows through the loop clockwise, then the face of the loop that we see acts like a south pole, and therefore the field lines are perpendicular to the loop and they must enter into the face, isn't it? That is downward into the table, you can say, because it acts as a south pole, and therefore field lines merge into the south pole is one answer. If you use the right hand thumb rule Then I'll explain it on the board, not on the board, in the PPT. Let us see. I think it is better to explain it on the board itself. I'll explain it on the board, and also read the next question. The magnetic field line in a given region is uniform. Draw a diagram to represent it. So both these questions I'll discuss on the board now. So here we have to consider a circular loop of wire. This is a circular loop of wire, and the current flows through this in a clockwise direction, plus minus. This is the current direction. Question is, the current passes through clockwise. Here it is, direction of the current. Apply the right hand rule to find out the direction of magnetic field inside and outside the loop. So within this loop, what is the direction of the magnetic field lines, and outside this loop, here and here, what is the direction of the magnetic field lines is the question. So by applying the right hand thumb rule here, imagine that we are holding a current carrying conductor in our right hand, pointing, the thumb points towards the direction of the current. In this case, the curly fingers, the wrapped fingers indicate the direction. So it is like this now here. So the field lines are like this at this point, and similarly here, if I hold like this, the field lines are this way, the field lines. So this is how it is. Okay, this is how it is. Outside, the field lines are coming like this outside. So within the loop, the field lines are merging into the loop. Those are entering perpendicular to the plane of the loop. So what is the first answer? Within the loop, the field lines are perpendicular to the plane of the loop and entering into the loop. That is, into the table. The field lines are entering into the table across the loop, within the loop, and externally the field lines are coming out, isn't it? Therefore, external to the loop, the field outside the loop, the field lines are perpendicular to the plane of the loop and coming outwards. Within the loop, the field lines are inward, entering into the table, and outside the loop, the field lines are perpendicular to the plane of the loop and outward. Inward, outward should be my answer for this question. Second, the magnetic field in a given region is uniform. Draw a diagram to represent it. Uniform magnetic field can be represented by equidistant parallel lines. So this represents a uniform magnetic field. These are the two questions. Let me check the next questions. Third one, choose the correct option is given. The magnetic field inside a long straight solenoid carrying current is 0, decreases, increases, is same at all the points. Here itself I'll explain. This is solenoid we have to draw. There is a current here. Question is, a current carrying solenoid produces a magnetic field. The magnetic field inside the long straight solenoid carrying current is it 0 inside the solenoid? No, because if I draw, see here, a current carrying solenoid acts as a bar magnet, and therefore the magnetic field lines are something like this. Okay, so inside you can see all these are parallel lines. I am not marking the arrow. In order to mark the arrow, I should apply the rule there, okay, the clock rule, because clockwise direction, anti-clockwise direction. If you want that also I can mark now. From this side, if this is the face here, if this is rotating like this, say for example, the current is entering this way, from here it is anti-clockwise, here it is anti-clockwise, and therefore it is a north pole, and therefore this is the south pole. So these are the directions here. Okay, now this behaves like a bar magnet. Inside the solenoid, the field lines are parallel to each other, hence it is uniform magnetic field. Uniform magnetic field. What is the question option we have to select? D is same at all the points, should be my answer for this. It is not zero, it does not decrease as we move towards the ends, no. It increases as we move towards the end, no. Is the same at all the points. Inside it is same at all the points, should be your answer. Next is, let us see. Example 13.2, we have already solved it. We will go to the next question. Yeah. Next is, which of the following property of a proton can change while it moves freely in a magnetic field? See the question, I will read it. Say my request would be, आप लोग textbook पे hold करिए in front of you. When I solve these questions, you must know where is this question, which is the syntax questions and all, and therefore it would be your effort to hold the textbook in front of you and read these questions. Okay, here, which of the following property of a proton can change while it moves freely in a magnetic field? A, mass, B, speed, C, velocity, and D, momentum. Which of the properties? In order to understand that, suppose this is a uniform magnetic field, and if the proton P plus is projected into this magnetic field, which properties of this proton change is the question. A, mass, B, speed, C, velocity, and D, momentum. Proton has got a mass of 1U, 1 atomic mass unit, and therefore it is quite heavier. So whenever it travels into the uniform magnetic field, it experiences a force because it is a moving charge, and moving charge produces electric current and thereby the magnetic field. So this experiences a force and the deflection. So as it experiences the force and the deflection, definitely out of all these parameters, which will change? The velocity will change. Can the mass of the proton change? No. Speed is, this speed is a scalar quantity. So magnitude of the speed changes. Whenever an object experiences a force, the velocity changes. Why it is so? Because the object will be under acceleration only in the presence of an external force. If there is no external force, according to Newton's first law, an object continues to move with a uniform velocity along a straight line, or it remains at rest, in a state of rest. Similar to that here, as the proton experiences the force, its velocity changes. Force causes the change in velocity. If the velocity of the proton changes, definitely momentum also changes, because momentum is the product of mass into velocity. Mass does not change, but the momentum changes. So options C and D are the two options for this one. I hope you have understood this. Next question. In activity 13.7, take it a little bit upwards. In activity 13.7, how do you think displacement of rod AB will be affected if current in rod AB is increased, a stronger horseshoe magnet is used, and the length of the rod AB is increased? In activity 13.7 means, here it is, A current carrying conductor when placed in a magnetic field, it experiences a force. That is, activity 13.7. You can have a look at this one and then I can take it. Don't disconnect, simply turn it and then take it back. This is the activity here. In this activity, I'll draw this diagram very quickly and explain this once again. So, here I'll draw. This is the conductor and this can be connected to, this is how the conductor, and north and south. This is the activity discussed here. See, whether current passes from here or from that side, it doesn't make any difference. What is the question? I'll read over here. In this activity, how do we think the displacement of rod AB, this is rod AB here, this is A and B, how does this rod will, how the displacement of the rod AB will be affected if current in the rod AB is increased? If the current is increased, magnitude of the displacement increases. See here, the force, magnitude of the force experienced by this is given by lib sine theta, or lib sine of 90 degrees, and therefore lib sine 90 is 1 and therefore it is lib. Therefore, the force experienced by a current carrying conductor is directly proportional to the length, directly proportional to the increase in current, and directly proportional to the magnetic field strength. Hence, question number 1, the displacement of rod AB will be affected if, how it is affected is the question, if the current in the rod AB is increased. If the current is increased, magnitude of the displacement increases because magnitude of the force increases. A stronger horseshoe magnet is used. P is increased. Stronger the horseshoe magnet, stronger is the force and hence more is the displacement. Length of the rod AB is increased. Force is directly proportional to the length. Increase in length causes the increase in force and thereby displacement. So by all three means, whether increase in the current in the rod AB, or stronger the horseshoe magnet, or the length of the rod if it is increased, in all these three cases, the force experienced by a current carrying conductor is directly proportional to the force, and therefore the deflection also will increase. That is the answer. Next, a positively charged particle, alpha particle, is projected outward west, projected towards west, is deflected towards the north by a magnetic field. The direction of the magnetic field is towards the south, towards east, downward, upward. What do you understand by this? Now, I am considering this board as the page here. Page I am reading from the textbook. With reference to the page, I will be able to explain this. A positively charged alpha particle is projected towards the west. So I should first mark the east, west, north, south directions. Here I will mark north, south, east, west. So a positively charged particle, that is alpha particle, is projected towards the west. Positively charged particle is projected towards the west. It is deflected towards the north by the magnetic field. So this positively charged particle, this one, when it is projected towards the west, it gets deflected. How this gets deflected? Like this. It gets deflected. That is in the direction of north. The deflection is towards the north. The direction of the magnetic field is, where is the direction of the magnetic field? Four options: towards south, B, east, towards east, C, downward and upward. Downward and upward. A moving charge produces a magnetic field, and when it is brought in the vicinity of the magnetic field, it experiences a force. The direction of deflection can be given by Fleming's left hand rule. So let me apply the Fleming's left hand rule for this one. Okay, there is a left hand rule in order to find the direction of the magnetic field. Now, the protons or the positively charged particle, whether it's a proton or alpha particle, doesn't make any difference. Alpha particle we'll consider because it is given in the question. It is projected towards this way, towards the west, and therefore the direction of the current is also in the direction of positively charged particles, which I have discussed. This is the direction, and this is deflection is towards the north, means the deflection is towards the north. This is deflection. Deflection means M, motion or force. In this case, I know the current, I know the motion, current I know, field is the question. Field, direction of the field is the question. Let us apply the Fleming's left hand rule. Current this way, therefore middle finger this way, this is the middle finger. Deflection top, yes, thumb gives the motion or the deflection, top. In this case, see here, in this case the field is out of the board, out of the page, that is upward out of the page is the answer. Therefore it is upward out of the page, that is the answer. Can you see here, this is the field. I have aligned the direction of the current middle finger from here to here, east to west, aligned. Deflection is from towards the north, that is the thumb points towards the north, and therefore this finger here, you can see it is pointing towards you, meaning the direction of the magnetic field is outward or upward from the page. Therefore answer is D here. Okay, yes. Next question. State Fleming's left hand rule. States Fleming's left hand rule. When we stretch the first three fingers of the left hand such that finger, if the forefinger indicates the direction of the field and the middle finger indicates the direction of the current, in that case the thumb indicates the direction of the force experienced by a conductor and thereby the displacement or the motion of the conductor. That is the Fleming's left hand rule. And what is that it is used for? It is used to identify the direction of motion of a current carrying conductor when it is placed in a magnetic field. Next question. What is the principle of an electric motor? This is what I said is the principle, that is a current carrying conductor when placed in a magnetic field experiences a force and thereby the deflection, and this is the principle used in electric motor, because in an electric motor a coil is placed inside the magnetic field, and when a current is passed through the coil also acts like a magnet, and this experiences the force in the presence of magnetic field and therefore it undergoes deflection. So that is the principle. So how to say this once again? A current carrying conductor when placed in a magnetic field experiences a force and thereby the deflection is the principle used in electric motor. What is the role of split ring in an electric motor? Split ring acts as a commutator that reverses the direction of current in a coil every half cycle. That is the answer for that. Next in text questions we'll see. Yes. Explain different ways to induce a current in a coil. Explain different ways to induce a current in a coil. So there are two ways by which we can induce a current in a coil. Of course, 2-3 ways you can write. One is this way. Yeah. By moving a magnet inside a solenoid is one way to induce a current in a solenoid. Also, you can say by moving a coil inside a magnetic field, or current can be induced by moving a coil into a magnetic field. That is the first method. This is the first method. And second method, as it is given in your textbook, I will apply the second method here. What is this method? Here there are two coils, primary coil and secondary coil. By changing the magnitude of the electric current in primary coil, a current can be induced into a secondary coil. That is the second method. So you can say whatever I explained this way, or you can a little bit modify this answer something like this. Electric current can be induced into a coil when it is brought into the vicinity of another coil in which the current is changed, or in which the magnitude of the current is changed. So, or also you can say, if the current is changed, if the magnitude of the current is important, okay, that is important. If the magnitude of the current is changed in one of the coils, then a current is induced into a neighboring coil due to electromagnetic induction. So these are the two methods by which you can induce a current into a coil. One more thing also you can say, here I said a solenoid, and you can talk about the coil also, something like this. If the coil is made to move in a magnetic field, a current is induced into the coil. If a solenoid is made to move into a magnetic field, a current is induced into the coil. And by changing the magnitude of the current in one of the coils, in one coil, a current is induced into another coil which is kept nearer to, in the vicinity of the first coil. We can say these are the three methods. Next, state the principle of electric generator, electromagnetic induction, which states that whenever there is a change in magnetic flux associated with a coil, an EMF and hence a current is induced into the coil, is the principle of an electric generator. Name some sources of direct current. Battery, cell, solar cell, DC generator are the sources of direct current. Which sources produce alternating current? AC generator produces alternating current. Choose the correct option. A rectangular coil of copper wire is rotated in a magnetic field, a rectangular coil. The direction of the induced current changes once in each 2 revolutions, 1 revolution, half revolution, 1/4 revolution. We have seen in AC generator the direction of the induced current changes 2 times in 1 cycle, means once in a half cycle. Therefore, answer option C, half revolution, is the answer for this question. Next, name 2 safety measures commonly used in electric circuits and appliances. The 2 safety measures are, one is earthing and second is fuse. Why these are the 2 safety measures? Earthing provides the least resistive path for the flow of current. Whenever there is a leakage of current to the bodies of the appliance, in that case, that current, the leakage current flows through the earth wire, and thereby it prevents the electrocution or severe shock to the person who handles the machine. I hope you are able to understand what is this earthing. Earthing, first of all, earth is maintained at 0 potential. Earthing provides the least resistive path for the flow of current. Whenever there is a leakage of current to the body of the appliance, that current flows to the earth and thereby it prevents electrocution of the person who handles the machine. That is the answer. Fuse. How the fuse protects? If there is an unduly high current flowing through the circuit, then the fuse melts by Joule's law of heating, based on the principle of Joule's law of heating, and thereby cuts off the power supply to the appliance or the circuit, and thereby protects the circuit. This is the answer. Next, an electric oven of 2 kilowatt power rating is operated in a domestic electric circuit of 220 volts that has a current rating of 5 amps. What result do you expect? Explain. So an electric oven of 2 kilowatt power rating is operated in a domestic electric circuit with 220 volts, which has a current rating of 5 amp. See, meaning, here I will try to explain that. The current rating of the main supply is only 5 amps. What is the power rating of an electric oven? Electric oven power is 2 kilowatt and voltage is 220 volts, and current of the power supply is only 5 amps. That is a given, 5 amps. So question is, what result do you expect? Explain. Meaning, there is a cable here which supports, there is a cable and there is a fuse of 5 ampere, and the electric oven's rating is 2 kilowatt and 220 volts, but there is a line that gives you only 5 ampere current. In this case, what would you expect to happen is the question. Let me calculate the current rating of the appliance at the rated power and rated voltage. So P equals V into I. So I equals P by V. Power is 2000 watts divided by 220. This is how it is. 2 11s and 2 1s. Okay, 11, which is approximately 9.0, something like this. Is it something like this? Let me check it. Power rating is 2000, it is correct, divided by 220 volts. .09 amps. As the supply current is only 5 amps, and as the equipment draws, electric oven draws 9 amps, the fuse in the circuit will melt by Joule's law of heating, and electrical power is cut off, and the electric oven does not function. Did you understand why it is so? If this is 2 kilowatt and 220 volts, then the rated current for this electric oven is 9.09 amps. But the circuit is able to provide, or circuit can withstand only up to 5 ampere current, and therefore the oven doesn't function at all, because the fuse in the line will melt. Why it is so? It will blow off. Why it is so? Because 9 amps current is flowing, which is more than the 5 amps, and therefore by Joule's law of heating, if there is more current, then the fuse must blow off. In this case, the fuse melts, blows off, and cuts off the electric power supply. Oven doesn't work. What precautions should be taken? Next question, third one. What precautions should be taken to avoid overloading of domestic electric circuits? In order to avoid overloading of domestic electric circuits, more appliances should not be connected to a single socket. That's all. That's the answer for this. Exercise questions. Which of the following, now we have completed the in-text questions. We'll go through the exercise questions. Which of the following correctly describes the magnetic field near a long straight wire? The field consists of straight lines perpendicular to the wire? No. Field consists of straight lines parallel to the wire? No. Field consists of radial lines originating from the wire? No. The field consists of concentric circles centered on the wire? Yes. Option D is the correct. Second question. The phenomenon of electromagnetic induction is the process of charging a body? No. The process of generating magnetic field due to a current passing through the coil? No. Producing induced current in a coil due to relative motion between the magnet and the coil? Yes, it is electromagnetic induction. The process of rotating a coil in an electric motor? Wrong. Option C is the correct one. The device used for producing electric current is called a generator. Next question. The essential difference between AC generator and DC generator is that there are four options. Between AC generator and DC generator, only the commutator is a different one. Why it is so? In AC generator, we have seen we use slip rings, whereas in DC generator we use commutator rings, which are nothing but split rings, and therefore the option D, AC generator has slip rings while DC generator has a commutator, is the answer. Now, at the time of short circuit, the current in the circuit reduces, does not change, increases heavily, vary continuously. Option C, increases heavily. Because of the short circuit, the fuse comes to the rescue. Because what is short circuit? When a live and neutral wire come directly into contact with each other due to damage of insulation, etc., then the current in the circuit increases very heavily, by which it may harm the appliances or it may lead to the fire accidents also. In order to prevent, we use a fuse there. Here the question is, at the time of short circuit, the current in the circuit increases heavily. Option C is the correct answer. State whether the following statements are true or false. An electric motor converts mechanical energy into electrical energy. Is it correct? Electrical motor converts mechanical energy into electrical energy. Is it true? No. A motor is the one which converts electrical energy into the mechanical energy. Isn't it? So first one, electric motor converts mechanical energy into electrical energy, is false. Second one, an electric generator works on the principle of electromagnetic induction. True. The field at the center of a long circular coil carrying current will be parallel straight lines. Yes, true. A wire with a green insulation is usually a live wire of an electric supply. Wrong. Green indicates earthing and the red wire indicates, just a moment, a red wire indicates the live wire, black neutral, green earthing. List three sources of magnetic fields. What are the sources of, list three sources of magnetic field? What he is asking, which question? List three sources of magnetic field. A current carrying conductor produces a magnetic field. A bar produces a magnetic field, and a solenoid produces a magnetic field. Just a moment, I'll look at the answers. I'll be referring Rachana Sagar, something like that. These are exercise questions. Exercises, yes. List three methods of producing magnetic fields. Okay. Bar magnet, okay, straight wire carrying a current, okay, and a circular coil carrying current. All these will produce magnetic field. Also you can say solenoid, that is a copper wire, a solenoid carrying current also produces the magnetic field. A straight wire, a coil and a solenoid, all these three produce magnetic field if an electric current passes through them. Along with that, you can add bar magnet also. Next, how does a solenoid behave like a magnet? Can you determine the north and south poles of a current carrying solenoid with the help of a bar magnet? Yes. A solenoid, whenever an electric current is passed through a solenoid, it acts like a bar magnet, and if it is freely suspended, it points towards the geographical north and south poles. How do you determine the north and south poles of a current carrying solenoid with the help of a bar magnet? It is simple. See here, probably you can explain with the diagram. This is a, I think I have drawn here, we can take here. Now this is a solenoid, let us make it a solenoid, means I have to connect it to the electric supply, battery plus minus. Okay. Now, how you have been given a bar magnet here, okay, you know north pole and south pole. How do you identify which are the poles of the solenoid is the question using this bar magnet. Bring the north pole of a bar magnet towards one of the faces of the solenoid. If it repels, then that face is the north pole, and the opposite face is the south pole. If it attracts, then that face is the south pole and the opposite face is the north pole. This is how you can identify using a bar magnet the polarity of or the north pole and south poles of the bar magnet, isn't it? Next one. When is the force experienced by a current carrying conductor placed in a magnetic field largest? When is the force experienced by a current carrying conductor placed in a magnetic field is largest? Here, this one. A current carrying conductor, when it is placed perpendicular to the magnetic field, then the force experienced by the conductor is largest. That is the answer. 10th one. Imagine that you are sitting in a chamber with your back to one wall. An electron beam moving horizontally from back wall towards the front wall is deflected by a strong magnetic field to your right side. What is the direction of the magnetic field? Here, I think it is better to explain this way. Okay. I am standing over here. There is a wall in the front and there is a back. An electron beam is projected from back wall to the front wall. This is a back wall. This is a front wall, back wall, and the electron beam is projected from back to front, electron beam, and therefore the direction of the current is opposite to the flow of electrons. Current direction I came to know. If this, and of course there is a magnetic field in this one, because into the magnetic field an electron beam is directed. So imagine that you are sitting in the chamber with your back to one wall, that is my back wall. An electron beam is moving horizontally from back to front wall. If it is deflected by a strong magnetic field to my right side, this is my right side. If this is deflected towards the right side, okay, what is the direction of the magnetic field? Current, deflection, I know. Magnetic field is the question. Let us apply Fleming's left hand rule. Okay, left hand rule. Direction of the current, MFC, motion field current. I need to find out the direction of field here, means forefinger I should know. I know the direction of the current from front wall to back wall. Middle finger I'll arrange it, or I'll hold this, it is better. Okay, here thumb deflection, field, current from this wall to this wall. So the current is from this wall to this wall. Yes, it is the middle finger. Deflection is towards you because it is towards the right side. It is said because I am sitting here, electron beam is coming towards my right side, is a deflection. Therefore thumb should point towards this way. Current, thumb towards you. I hope now you will be able to see partially. This is the current here and thumb here. The direction of the magnetic field is pointing downwards. Is it right? It is pointing downwards. So what are the options here? Let's see. So what is the direction of the magnetic field? The direction of the magnetic field is downwards, that is from ceiling to towards the floor is the answer. Next question. Draw the level diagram of an electric motor. Explain its principle and working. What is the function of a split ring in an electric motor? Yeah, that we have discussed. You can draw the label diagram and explain it. Please hold the question. Question number? Draw the level diagram of an electric motor. Explain its principle and working. That I have already discussed. You can note down from that. What is the function of a split ring in an electric motor? A split ring acts as a commutator. It reverses the direction of the current in a coil every half cycle. Question number 12. Name some devices in which electric motors are used. Washing machines, fans, MP3 players, etc. Question number 13. A coil of, now no need to move anything. A coil of insulated copper wire is connected to a galvanometer. Okay. What will happen if a bar magnet is pushed into the coil? Current is induced. Withdrawn from the inside the coil, current is induced. Held stationary inside the coil, no current is induced. That is the answer for that. Two circular coils A and B are placed close to each other. Okay, here like this circular. These are also coils, or you can also say, a coil is where anywhere. Did I draw the coil here? No, I draw the coil also. This also you can call coils only. Two circular coils A and B are placed close to each other like this. If the current in the coil A is changed, let me mark this as A and B. If the current in the coil A is changed, will some current be induced into the coil B? Yes. Give reason. Due to electromagnetic induction. Isn't it? That's the thing. 15th. State the rule to determine direction of magnetic field produced around a straight conductor carrying current. Right hand thumb rule you can define, already that we have discussed. Force experienced by a current carrying conductor placed in a magnetic field which is perpendicular to it, that is Fleming's left hand rule. Current induced in a coil due to its rotation in a magnetic field, that is Fleming's right hand rule. All these rules I have discussed and you can refer back once again. Explain the 16th question. Explain the underlying principle and working of an electric generator by drawing a level diagram. What is the function of brushes? So underlying principle for working of an electric generator is electromagnetic induction. And what is the function of brushes here? The brushes provide, what is the function of brushes? Brushes establish a contact between the slip rings and the external circuit, and thereby they establish the conductivity, you can say, or you can say brushes establish the conductivity between the coil and the external circuit. I think that is excellent. What is that? Brushes establish the conductivity, electrical conductivity I am talking about. Brushes ensure the flow of electric current between the coil and the external circuit. That is the answer for that. What does an electric short circuit, when does the electric short circuit occur? When a live and neutral wire come directly into contact due to damage of insulation, short circuit takes place, and in that case abruptly the current rises in the, abruptly the current increases to a very high current in the electric circuit. What is the function of an earth wire? Why it is necessary to earth metallic appliances? The function of the earth wire is to provide the least resistive path for the leakage current. Whenever the, why we should connect the metallic appliances? The bodies of the metallic appliances should be connected to earthing wire. If there is a leakage of the current from the live wire to the metallic body, in order to prevent the electrocution, if the earthing wire is connected to the body, then the leakage current flows to the earth, and the person handling the appliance is prevented from electrocution. So, dear students, these are the question answers of your textbook, and my request would be you go through some exemplar questions If you have any difficulty, you please get back to me, and whenever time permits, I'll be picking up few questions from the exemplar book and I'll be discussing, because many times many students, to digest this itself, they take a lot of time. Sometimes they may not go through the exemplar questions. So my request would be, you try your level best. First you put efforts and then you ask me the question if you are not able to understand when you go through the exemplar question. So this chapter is complete in all respects. That is chapter number 13, magnetic effects of electric current. We have completed in all respects, including the question answers, and even we discussed the generators part also, AC generator, DC generator, and the working principle, construction, etc. Okay, so this chapter is complete in all respects. I'll end the lecture over here and see you in the next lecture with a new chapter. Thank you very much for watching.